All right, today we're going to pull back the curtain on the invisible architecture that pretty much runs our digital lives, databases. You know, they're the unsung heroes that keep your social media feed scrolling and your online shopping cart from, well, exploding. So let's just dive right in. But seriously, just stop and think about it for a second. Every single like, every purchase you make, every new friend you add, that's all a piece of data. How does it all get stored and found and linked together in like a fraction of a second? Well, the secret is a journey from complete and utter chaos to this really elegant, structured clarity. And to really appreciate that clarity, we have to start with the mess. Just try to imagine a huge company trying to run its entire operation from like a single giant, totally disorganized filing cabinet. Papers are everywhere, there are copies of the same thing stuffed in random folders. Believe it or not, that's kind of what early data storage was like.
So on one side, you've got this old file-based approach. Each app has its own separate files, and they often have the exact same information copied over and over again. I mean, it is a recipe for disaster. But on the other side, you have the relational database, where all the data lives together in one structured system, with these really clear links between all the related info.
This old way of doing things, well, it commits three major sins. First up, data redundancy. You've got the same piece of data stored in multiple places, just wasting space. Then you have data inconsistency. So what happens if you update a customer's address in one file, but you forget to update it in another? Which one's right? And finally, there's data dependency. This one's a killer. Changing the structure of just one file could completely break every single application that relies on it.
So, how did we fix this absolute mess? Well, we needed a revolution, a whole new way of thinking. We needed a system that wasn't built on isolated files, but was built on relationships.
And that brings us to our hero, the relational database. It's way less like that messy file cabinet and a whole lot more like a perfectly organized library, where every single piece of information has its own specific place and is logically linked to everything else it relates to.
The basic building blocks are actually pretty simple. Data is organized into tables, which, well, they look just like spreadsheets. Each record, or row, represents a single item, like one specific customer. And each attribute, or column, is a piece of information about that item, like, say, their name or their email address.
Now, here's where the first bit of real magic happens, the primary key. How do you make absolutely sure every single customer or product is unique? Simple. You give it a unique ID. It's just like how no two people have the same driver's license number, right? Well, no two records in a table can have the same primary key. It is the ultimate unique identifier. Okay, so if we have all these nicely organized tables, how do we actually link them together? Well, that's the job of the foreign key. It's really just the primary key from one table placed into another table to create a relationship. This is the magic pointer that connects, for example, a customer to all of their orders. Let's make this real. Look at this. In our customers table, you can see that customer ID is the primary key. See how each number, 1, 2, 3, is totally unique? Each one points to exactly one person. Super clean, super simple.
Okay, now watch this. Over in the orders table, we see that customer ID column again, but here it's not the primary key. It's a foreign key. See that value of 2 in the first row? That creates a direct link right back to Jane Doe in our customers table. This is how we know exactly who made which order without having to repeat all of their personal information over and over again. It's brilliant.
This whole system is held together by this one super important rule called referential integrity. All it means is that you can't have an order with a customer ID of 99 if there's no customer 99 in the customer's table. It prevents these orphan records, data that doesn't link to anything, and it's absolutely fundamental to keeping the data trustworthy. Now, creating these tables isn't just a free-for-all. There's a formal process for organizing them in the most efficient way possible, and it's a process known as normalization. You can think of it as the art of tidying up your data.
Normalization is basically a step-by-step process. Each of these three normal forms adds a new logical rule to make our data structure more robust and completely free of that nasty redundancy we talked about. So let's just walk through the big ideas real quick.
All right, first normal form. It has one simple rule. Get rid of repeating groups. You can't stuff multiple values into a single cell. Every single entry has to be atomic, just one thing. Okay, look at this messy table. We've got one student, John Smith, but he has 3 different subjects and 3 different teachers all crammed into his one single row. This is a classic repeating group, and it's basically impossible to work with efficiently. So, to fix this, we split the data. The student's main info stays in a student table, and all those repeating subjects, they get moved to their very own table. Now, each cell holds exactly one piece of information. So much cleaner. The next step, second normal form, is all about making sure all the data in a table truly belongs there. Every single attribute has to relate to the entire primary key, not just a little piece of it. This rule basically forces us to store information in the most logical place possible.
And the final cleanup step, third normal form, says that secondary bits of info can't depend on other secondary bits of info. For instance, a professor's office number belongs in a professor's table, right? It doesn't belong buried in a student's enrollment record. It's that final step to weed out the last little bits of redundancy.
So we have this beautifully organized, normalized database. Awesome. But how do we actually, interact with it? Well, we need 2 things. We need a manager and we need a language.
The manager is the Database Management System, or DBMS for short. This is the powerful software that sits on top of all the data. It's the bouncer, the librarian, and the administrator all rolled into one. It handles security, ensures data integrity, manages who gets access, performs backups. It's basically the operating system for our database.
And the language we use to talk to the DBMS is called SQL, which is kind of split into 2 parts. Think of it like this. Data Definition Language, or DDL, that's the architect's blueprint. It's what you use to build the actual structure, the tables and columns. Then there's Data Manipulation Language, or DML. That's for working inside the building, adding, retrieving, and updating the actual data. Here's what a DDL command looks like. Don't let the code scare you. This simple line, create table, is just the instruction that tells the DBMS to build the student table, and it specifies what each column should be named and what kind of data it'll hold.
And this is a DML command in action. This is how we actually ask the database questions. Select tells it what we want, from tells it where to look, and where filters the results. So this command is just asking for the first and last names of all the students in class 7A. It's a really powerful but also readable way to chat with our data.
Okay, so let's pull this all together. Why on earth do we go through all this trouble, all these keys and relationships and these weird normalization rules?
Because it gives us incredible benefits. It gives us data integrity, which means the data is reliable. It minimizes that redundancy, which saves space and prevents a ton of errors. It maintains data consistency across all our apps. It creates data independence, so we can actually change the database structure without breaking everything that uses it. And of course, it gives us robust security. We've basically solved all 3 of those sins from the old file-based approach.
From your online banking to your social media feed, our entire digital world is built on this foundation of organized relational data. So the final thought I'll leave you with is this. If all these rules of database design just vanished tomorrow, what would be the very first thing in your digital life to completely and totally break?